very much. Today I'm going to talk about my work in progress with Diaz Maceda about manifolds with boundary, especially using multisymplectic formalism for computing the dynamics of fields in this kind of manifolds with boundary. This is interesting because we have several examples of manifolds with boundary in which the dynamics of fields over there gets non-trivially affected by the presence of the boundaries. For example, in this case, where we have a line attached to a point on one side and free on the other, or this other example in which we have a vibrating membrane in which the boundary is fixed. These kind of systems make us wonder these two questions. First of all, how can we encode the boundary conditions at the level of the action? And second of all, what is the geometry describing the dynamics in manifolds with boundary? In order to solve these questions, we are going to first introduce relative cohomology, which is going to be the idea, the mathematical idea behind all the geometry describing the dynamics of our fields. Then a variational problem. With this variational problem posed, we will introduce the definition of multisymplectic manifolds with boundaries. Then, with this definition, introduce the Hamilton relative form. And finally, we will see the particular case of the Lagrangian formalism, which is a particular case of the variational problem, and some final examples. So with this, let's start with relative cohomology, for which we start with a manifold M, and we have its boundary, denoted here in red, in such a way that, following the lines of Margalev that gave an incredible talk in Miraflores last year, we are going to postulate the Stokes theorem in the work, which has this expression, and on the boundary we write the same expression for the Stokes theorem, but on the left-hand side is 0 because the boundary of the boundary is 0. We can reorder these integrals written in this way, and let me introduce a notation in which the integral of pairs of form over pairs of space is just going to be the difference. With this notation, we can rewrite the Stokes theorem this way, and finally a second notation, the exterior derivative of pairs of forms is going to be this expression, so that it's the same expression we have in the integral, and we just simplify this way. In this sense, we are writing the Stokes theorem all in the left-hand side, and with this new cohomology, which is called the relative cohomology, this behaves as a manifold with its boundary doesn't have this relative boundary because there is nothing on the other side of this integral, of this Stokes theorem. So the properties of this relative cohomology: first, its derivative acting twice is 0 as expected, so it defines actually a relative cohomology. Second of all, it has a dual homology given by this operator, which satisfies this relativization of the Stokes theorem. Third of all, this relative boundary acting twice is 0 as expected. But in this case, the relative boundary of a manifold with its boundary is 0. So, in this sense, this manifold with its own boundary behaves as if they doesn't have relative boundary. 5, I will make a new definition, which is the contraction over pairs of form, which is just given by this expression. Okay, so let's start with the problem. We have the boundary, which is a manifold embedded on the bulk via an embedding. This is an n-1 dimensional manifold. This is an n-dimensional manifold. And over M, we are going to put a locally trivial fiber bundle having as coordinates the fields and the coordinates. With this diagram, we can compute the pullback bundle, which is just the restriction over of the locally trivial fiber bundle to the boundary, which has these coordinates. We can take one section psi on the bulk, and this canonically restrict to the section on the boundary. And finally, we are going to make a final definition, which is the pullback of pairs of form, which is just given by this formula. So with this, we can pose the problem of calculus of variation, which is we have a locally trivial Fourier bundle and a boundary like this. So we are going to take two forms, one n form and one n minus form, one n form in the bulk and one n minus 1 form on the boundary, and we are going to integrate them over the bulk and the boundary to form this function. This is going to be the action. So the problem consists in to find the section C, which are a critical point of this function. In order to do this, what we are going to do is compute the variation of the action after a bit of computation that I don't want you to solve, to see. And using the definitions that we just introduced, we see that the variation of the action is just given by this formula. And using, well, if we want this action to be at a critical point, we need this variation to be 0 for every vector field, and using techniques similar to the fundamental lemma of calculus of variation, it means that this integrand has to be 0 for every vector field. So these are the equations of motion. And following the guidelines of multisymplectic formalism, we define the multisymplectic relative form, which is this pair of forms, as the exterior relative derivative of this pair of forms, in such a way that its exterior relative derivative is 0 because the relative exterior derivative acting twice is always 0. So this motivates us the following definition. A manifold with boundary is called multisymplectic if it's endowed with a relative form such that its relative exterior derivative is 0. Now, with this definition, I'm following some textbook on multisymplectic formalism. For example, this one that I strongly recommend for people that are introducing to multisymplectic formalism. We can define locally Hamiltonian multivector fields are those whose contraction by the relative form is closed with this new relative cohomology, and in such a way that these are the symmetries of the geometry, because when taking the derivatives of the multisymplectic relative form, this is going to be 0 because of definition of multisymplectic formalism, and this is going to be 0 by assumption, so this is what I said, asymmetry of the geometry. We can do the same with globally Hamiltonian multivector fields, which are those for whose this contraction is not 0, but is exact, and this differential form F is going to be called Hamiltonian relative form associated to the vector field X. We can define a bracket similarly. If we take two relative forms, it's going to be the Schatten-Nijenhuis bracket of the Hamiltonian form associated to the Schatten-Nijenhuis bracket. In such a way that we can compute, after a bit of computation, the form of this Poisson bracket. Well, not necessarily Poisson. We are researching this still. Of this bracket, it has this expression. We can define conserved quantities. On the other hand, we can define conserved quantities as a relative form whose pullback by solutions of its differential is 0. And there is a theorem very similar to the Neredes theorem in mechanics that says if if X is a globally Hamiltonian vector field, then its associated Hamiltonian form is going to be a conserved quantity. This is very easy to prove, just by definition of Hamiltonian associated form. We can take a pullback by a solution, and this first term is 0 because of the equations of motion. So this is a conserved quantity. This kind of conserved quantities can be integrated over manifolds, over some manifolds of the bulk and the boundary, in such a way that we define the total charge as this integral. There is a theorem similar to the conservation of this total charge that says that if two surfaces, these two submanifolds surround some volume, then relatively some volume, then their charges are going to be equal, which is easy to prove just by definition and using some brief computation using the Stokes theorem. This first term is zero by assumption because this is a conserved charge, so the charges are going to be equal. This is very interesting in physics. If we have a universe of the form of a cylinder with lower and top covers and lower and top cylinders, and everything covered by a shell, then the relative boundary of the bulk and the shell, or the full cylinder and the shell, is going to be, it happens to fulfill the assumption of the theorem. So the charge, if we have a conserved charge, the total charges on sigma 1 is going to be the same as the ones on sigma 2. So let's move now to the Lagrangian formalism. We had previously this commutative diagram, and we are going to extend this diagram with the jet bundle of E, which is the geometric space encoding the derivatives of the section as independent variation in this way. And we are going to take the pullback bundle, which is just a restriction in this case, having these coordinates, but I make you notice that this is not the jet bundle of E on the boundary, because here we have velocities normal to the boundary. We can take a section and a section on the boundary, and we say that a section is an holonomic section is if the velocities are the derivatives of the field. So the problem in this formalism, the Lagrangian problem in this case is the same. We have a fiber bundle and its boundary, and we are going to take a Lagrangian on the bulk and a Lagrangian on the boundary, which are a priori independent. There is no relation between each other, and especially, in particular, different choices of the Lagrangian on the boundary will lead us to different boundary conditions, and we are going to form this differential form, n minus 1 relative form, that we are going to integrate to define the following functional, which is going to be the action. And the problem consists in to find the holonomic section, which is a critical point of this function. So, in order to do this, we express the action in the typical way, and we are going to take a holonomic preserving variation of the fields, and take the variation of the action in the bulk, the variation of the action on the boundary. The variation of the action in the bulk can be integrated by parts in the usual way, leading to the Euler-Lagrange equations of motion, the Euler-Lagrange equation, and one boundary term that will contribute to the boundary in the future. But, however, the variation of the action on the boundary cannot be integrated by parts, because here we have velocities which are normal to the boundary, which cannot be integrated by parts. So, in order to take care of this, we are going to first split the derivatives in its tangential and normal components by introducing the normal one form and normal vector fields. Oops, this should not happen.
Yes. Okay.
Well, that's weird. Can you close and open it again, maybe?
Yes.
I promise I tried a lot in my house and it worked perfectly.
Okay.
Actually, yesterday that we could go to the final and there was no problem.
Okay, so something else.
Yep. After this?
Okay, it was after this, yeah. We did a bit of computation, we integrated by parts, and we introduced the normal and tangential components to to separate the derivatives. Yeah, and we can define the projector to the tangent space.
Maybe go there, click to the next slide.
I don't think we can we can go to the next slide.
Shall we just
Yeah,
let's close the entire.
Different browser, let's try it.
Yeah. Let's try. Where's the file saved?
Oh, it's on the desktop.
Okay, let
So
Can I ask you a question?
Yeah, for sure.
just close all
In
tabs.
example condition is like,
Yeah.
you had sigma 1, big sigma, and small sigma.
Yeah.
The big sigma being the plates,
Yeah, exactly.
and the sigma 1 is
Are
the
the
boundary
After
of
19.
Yes.
not all the cylinder, just of the plates, right?
Just all the data.
The charge,
The charge have a contribution integrated on the wood, in the wood and on the wood.
yes, but the conservation is in between sigma, the small sigma 1 or the big sigma 1. Sorry, the big
I mean,
sigmas or the small
The
If
charge
you're missing
has
it from-
two. The charge has two contributions.
Yes.
The charge is the sum of the bulk term and of the boundary term.
It will still be recording, right?
Over there. And the sum of the two integrals
Okay,
is the one that is conserved.
thanks.
Okay,
So
now.
I think we managed to go past
Yeah.
the broken bit.
Okay, so well, what I did here is I introduced the projector to the tangent space and the normal space. The normal derivatives and tangential derivatives, and the normal derivatives cannot be integrated by parts at all, but the tangential derivatives can be integrated by parts, leading to this term. This term is the left, which is integrated by parts, and we have this other term that couldn't be integrated by parts. So with this, we have this final. We have this final contribution to the variation of the action. One first contribution in the bulk, one second contribution on the boundary, which is proportional to the variation of the fields, and a third contribution that is on the boundary and it's proportional to the normal derivative of the fields. And in order for this action to be in a critical point, we need and we proved that using similar techniques of the fundamental lemma of calculus of variation, we proved that these three equations has to be satisfied independently, leading therefore to the Euler-Lagrange equations in manifolds with boundary, which has these expressions. So let me return a bit to the action, which has this general expression. Before, in the last section, I said that the general expression for the equation of motion were this one. However, one could think that with this new Lagrangian, the equations of motion are just this. However, this is not true, because this expression were valid for a general vector field, but now this vector field is a particular one, which is a holonomy preserving vector field. And some of the arguments could not be repeated in this case. However, it could be very interesting if we have some differential form which happens to fulfill this equation and recover with this equation the equations of motion. In such a case, we call this the Poincare-Cartan relative form. This Poincare-Cartan form has to first be Lepage equivalent to the Lagrangian pairs, and second of all, it has to bear information on the integration by parts. For the first one, it's a sufficient condition to ask that the pullback is the same for both. And for the second one, we are going to ask that the relative contraction of this Poincare-Cartan form is this expression, which is the term that we integrated out when integrated by parts in the derivation of the Euler-Lagrange equation. So the relative form satisfying these two properties, which is the Poincare-Cartan form, is this expression. With this Poincare-Cartan form, we can substitute it in the general equations of motion and for these two vector fields, we find two equations in the work, two equations on the boundary, which are the equations that we were searching for, except for the third one that adds no more information apart from the holonomy of the system. But the other three ones are the three Euler-Lagrange equations of motion in manifolds with boundary that we were searching for. Finally, some examples. We are going to start with the scalar field, which has this Lagrangian in the work, and we are going to take the Lagrangian on the boundary to be 0 in this case. Plugging these Lagrangians on the equations of motion, we lead to the first equations to the typical equation of motion of the scalar field, and however we find a new equation which fixes on the boundary, which fixes the derivative of the field to be 0. So in this case, what we are doing is fixing a Newman boundary condition for the scalar field. If we don't want the scalar field to have this boundary condition, this normal derivative to be 0, but any other function, we could plug any other Lagrangian of this form, and this will be the equations of motion on the boundary, fixing the normal derivative to be this other expression. Another example, the same scalar field, but using now this Lagrangian, we can plug these Lagrangians in the equations of motion, leading to the same equation of motion in the work, but however now the important one in the boundary is this third one, which fixes the bulk, which fixes on the boundary the field to be 0. So what we are doing is fixing Dirichlet boundary conditions. If we want this field not to be 0 but to be any other function that we want, we add this other term on the Lagrangian. For electromagnetism, we can do the same. We have these Lagrangians, and we can plug in the equations of motion, leading to the typical equation of motion of electromagnetism, but fixing this boundary condition on the boundary, which is kind of a Newman boundary condition, and using this other Lagrangian on the boundary, and plugging these Lagrangians in the equations of motion, and simplifying using that the normal is not like, then we have this other term which forces the tangential components of the electromagnetic field to be 0. So in this sense, this is like Dirichlet boundary conditions. Finally, some conclusion. First, that field theory manifolds with boundary can be described with multisymplectic formalism just by changing the cohomology to the relative cohomology, and changing all the definition of multisymplectic formalism just by changing differential forms by relative forms, based on relative forms, and changing the cohomology to the underlying one. That boundary terms in the action encode boundary conditions, different Lagrangians on the boundary encode, for example, Dirichlet or boundary or Newman conditions. And that dynamics of field theory are described by the Poincare-Cartan relative form. For the future, we would like to study second order Lagrangians, in particular for introducing to general relativity, to introduce edge and corner terms by changing again the cohomology to this other one, and to study the properties of the relative bracket and the Hamiltonian formats of these multisymplectic formats. So thank you very much. I am open to all your questions.
Questions?
I think you know what I'm going to ask, but I will ask it anyway. Have you given any thought to change contraction by vector fields to relative vector fields and this sort of stuff?
Yeah. There was actually the
Yes,
one in the I hope I can solve your question. Yeah, the thing is that yeah, we have here what we are looking is to the minimum of the section, the section that is a critical point of this function, in the sense that we are looking for the section in the bulk and the restricted to the boundary section. I mean, it's the same section, but integrated in the bulk and on the boundary, but via its restriction. So in this sense, the vector on the boundary cannot be free, cannot be any other, but has to be the restriction of this vector, because they are the same sections but restricted. So if you were looking for pairs of sections here and here that could be different, then yes, then these vector fields could be different. But in this case, that I'm looking for a section whose restriction minimizes the action, then I need it to be the restriction.
I see. Okay, so for the variations, it makes sense to restrict to the vector fields, but in principle, I could imagine that.
Yeah, in principle, if you are looking for sections that are not like this, it's interesting that you enlarge your set of vector fields.
Yeah, okay. Thanks.
Any other questions?
No.
Go ahead.
If we have, I didn't understand if you are, if this works for an arbitrary fiber band over M or just for the trigger one. Because in the diagram you were.
It's locally triggered.
This is going to be a strange question, but have you considered examples where the bulk Lagrangian is zero and you only have a boundary Lagrangian?
Oh, that will be very interesting. Let's see what will happen. Sorry for this. Wow. I think support is not going to let me. But probably you could.
Because I'm asking a question that I think I know the answer to. I think what you end up with is a Lagrangian multiform or pre-Lagrangian system, which is what some people in the room are very familiar with, and it occurs in integrable systems. Now, it's definitely not exactly the same, but I think both have a restriction in common. And we can have a chat later, but I might have some suggestions
Yeah.
that we can approach the higher order.
What it would happen is that your action is your action only contains bulk term. So what you're looking for is for a section that minimize your bulk interval. So probably you are going to have a lot of freedom in your boundary integral. You are going to have a lot of freedom